Good morning. Instead of closely following our text in Chapter 3, we take a different approach based on the industrial experience of your instructor. First, we narrow the application of algorithms to algorithms that can be implemented as computer programs. Second, we amplify our methods of demonstrating that statements about an algorithm are true to include testing on an actual computer. Definition 1. An algorithm is a finite set of precise instructions for performing a computation or solving a problem. Algorithms are expressed as computer programs. We will use the C++ programming language in this class to express algorithms. Definition 2. Algorithms are measured in terms of time complexity. The time complexity of an algorithm is a measure of how much time is required to execute an algorithm. We measure the time in terms of the number of operations performed to execute an algorithm. A function t of n is created for every algorithm. The function t of n is a measure of the time required to execute an algorithm. The parameter n is the size of the problem. Definition 3. The time complexity of the statements of a computer program are given by a set of heuristics or rules. Time complexity rule 1. The cost of subprogram prologues and epilogues is said to be 0. The cost of calling and returning from a subprogram is 0. Example 1. Find the time complexity of the program in figure 1. We have int main returns 0. Solution. Create a 3-column table, putting line numbers in the first column, statements of the program in the second column, and the cost of each statement in the third column. Sum the cost of the individual statements to find the cost of the program. In this case, the cost is 0. Int main represents the prologue, and return 0 represents the epilogue. The closing curly brace is just syntactic and contributes nothing towards the execution of the program. Example 2. Find the time complexity of the program in figure 2. What we have here is main, which calls a subprogram called do nothing. And since do nothing does what its namesake does, that is nothing, why we find that calling and returning from function do nothing costs nothing. Time complexity rule 2. Declarations cost nothing. So here we have our former program which just returns 0, and we have a single declaration where we declare integer a, but it costs nothing to declare the integer. Time complexity rule 3. Unit cost is assigned to all basic operations, including arithmetic, logical, relational, and assignment operations. Here in example 4, we have a main program where we have an assignment statement. A is assigned the value 1, and then another assignment statement. A is assigned a plus 1. If we look at our 3-column expression here, what we find out is on line 3 that we have a cost of 1. That is, the assignment operation costs unit costs. On line 4, we have 2 operations, assignment and addition, so that cost is 2. And the total cost of executing this program is 3. Time complexity rule 4. The cost of operations executed in the test of a while loop is accounted in 2 places. The cost of the test when it is true is accounted on the same line as the test, and the cost of the test when it is false is counted on the closing curly brace of the while loop. The bodies of all while loops are enclosed in curly braces. So here in example 5, we find that we have a very simple while loop. It has a single statement in there, a++. So we initialize a loop variable, int a is assigned 0, and then we have the while loop while a less than 10, and then we increment a inside the loop. So we see that our cost in line 1, the initializing of the loop variable, that's assigned 1 because there's only one assignment statement. Then what we do is we compute the cost of all of the comparisons formed on line 2. And what we know is that 10 such comparisons are performed. They are, A is compared to 10 when A has a value 0, when A has a value 1, when A has a value 2, on up to the value when A has a value of 9. When A has a value of 10, we compare 10 with 10 and we ask ourselves, is 10 less than 10? And the answer is no. So we don't account the cost of when the test A is less than 10 is false, only when the cost of the test is true. So the comparison, unit cost, is compared 10 times when A is 0 through 9. And so we assign a variable k to that, but the cost of that statement is 10. Since our test was executed true 10 times, so are all the statements in the body of the loop. So this increment of A is also executed 10 times, and an increment operation is counted as 1. So the total cost to execute this loop is 22. They have a cost of 1 when A is equal to 10, and we account that cost on the closing curly brace. Time complexity rule number 5. Computing the number of operations in a for loop is too complicated. We therefore transform a for loop into statements and a while loop as shown in the example before. Example 6. Split the for loop in the figure below into its component parts and compute the time complexity for each of the component parts as to be included in the time fragment. So here is our statement. For int a equals 0, a less than 10, a plus plus. So I place the initialization outside the loop, or just before the loop. I replace the loop test with a while test. I place the loop increment decrement just before the end of the loop body. And I be sure to make the loop body a compound statement enclosed in curly braces. And since this loop is the same as shown in example 5, it has the same cost. Time complexity rule 6. Always select the alternative having the largest time complexity value. Example 7. Find the time complexity of the code fragment in figure 7. If a is less than n, then a is n times a minus 1 plus n times n minus 1 times a minus 2, or else a plus plus. So what we assume is that we assume that the worst case, that is, that the most costly alternative is always executed. So in the true case, when a is actually less than n, our cost is 7, whereas when a is equal to n or greater than n, our cost is only 1. But for the purposes of time complexity, we always assume the greater cost.